Nelson Colón Vargas's study, The Traveling Mailman, presents a novel approach to user-centric redistricting, leveraging the US Postal Service network to quantify community connectivity. By integrating topological data analysis with Markov Chain Monte Carlo methods, this research assesses the impact of district boundaries on community integrity. Focusing on Iowa as a case study, the author employs KMeans clustering and stochastic rebalancing to generate and refine districting plans. The proposed method produces plans with fewer cut edges and more compact shapes than the official Iowa plan under relaxed conditions, suggesting potential inefficiencies in existing boundaries. A Gaussian Mixture Model analysis reveals three distinct distributions in the districting landscape, providing a more accurate reflection of community interactions and facilitating fairer political representation. This framework aims to address pressing issues such as gerrymandering and voting rights, ultimately enhancing user experience in the context of political districting. By applying topological optimization methods, this study offers a data-driven approach to districting, enabling the creation of more compact and contiguous districts that better reflect community connectivity. This novel approach has significant implications for promoting fair and representative districting practices. Districting, a fundamental problem in computational social science, can be revolutionized by integrating topological data analysis and K-means clustering. This approach builds upon a solid theoretical framework, defining key concepts such as districting, topological data analysis, K-means clustering, and Markov Chain Monte Carlo (MCMC) methods. The rationale for employing MCMC lies in its ability to efficiently sample from complex distributions, facilitating the exploration of the solution space. The methodology involves selecting an optimal p-value for the study, followed by stochastic rebalancing of K-means generated districts to ensure population parity. This process is reinforced by Monte Carlo Markov chain simulations, which provide robustness to the results. Furthermore, Gaussian Mixture Model analysis is employed to uncover underlying patterns in the data. The results section presents a comprehensive analysis of known variables and parameters, as well as the application of K-means clustering to generate initial districts. The rebalancing of these districts is then compared to the official district plan, revealing insights into the effectiveness of the proposed approach. Additional investigations provide further validation of the method. The discussion highlights the significance of the findings, including the ability to uncover hidden patterns in districting data. Notably, the approach overcomes traditional limitations of districting methods, offering a more nuanced understanding of the complex relationships between demographic and geographic factors. While limitations and potential avenues for future work are acknowledged, the novel approach presented in this paper has far-reaching implications for the field of districting and computational social science. Electoral districting is a critical process that shapes political representation and resource distribution, but it often faces scrutiny due to issues such as gerrymandering and inadequate representation. Traditional redistricting practices have primarily focused on population equality and political boundaries, resulting in districts that fail to accurately reflect community cohesion or interests. This paper introduces a novel approach to electoral districting by leveraging the postal network and employing persistent homology within topological data analysis (TDA). The postal network, optimized for equal access and connections, serves as a proxy for community cohesiveness. By utilizing a graph that captures more than just proximity among districts, this approach captures nuances beyond mere population counts. This method builds upon and enhances the work of Deford et al., who introduced a method for creating districts by cutting edges of the adjacency graph. However, their approach doesn't fully capture the true spatial distribution of populations within counties and assigns equal weight to all cuts, regardless of their impact on community connectivity. Inspired by the Waffle House Index used by the Federal Emergency Management Agency, FEMA, this novel approach provides insights into the impact of redistricting on community structures, offering a more nuanced assessment than conventional approaches. By considering the postal network as a proxy for community cohesiveness, this method has the potential to significantly improve the accuracy and effectiveness of electoral districting, ensuring that political representation better reflects the needs and interests of communities. This approach also enables the identification of critical community connections and the assessment of district boundaries' impact on community structures. By doing so, it provides a more comprehensive understanding of the electoral districting process, ultimately leading to more accurate and effective representation. Topological Data Analysis, TDA, is leveraged to introduce a novel approach to redistricting, incorporating postal networks as proxies for community structure. By applying persistent homology, community structures are captured across scales in the redistricting process. The postal network serves as a practical and efficient proxy for community focal points, enhancing the understanding of how severely a community has been affected by a natural disaster. Stochastic rebalancing KMeans, KMeans, is proposed for initializing district searches, extending the work of Defert et al. In evaluating district plans through Markov Chain Monte Carlo, MCMC, methods. By generating a large number of districting maps that meet selected criteria using MCMC techniques, the likelihood that an existing districting map could have arisen by chance is assessed. A case study in Iowa is presented, where the requirement to respect county lines simplifies computations. However, with increased computational power, this process could be extended to the census tract level. The key contributions of this research include the introduction of KMeans districts, the integration of TDA with redistricting, the novel use of postal networks, and the extension of MCMC-BASED district plan evaluation. The novel algorithm for redistricting utilizes a theoretical framework and definitions to ensure optimal district configurations. It considers factors such as population size, geographic continuity, and community cohesion. The approach leverages the postal network, with cut edges serving as a measure of community integrity. An optimization method was developed to minimize these cut edges within set parameters. The data collection and code for this study are available on a GitHub repository. The pseudocode of the algorithms used can be found in the appendix. The theoretical framework includes definitions for electoral districts, collections of districts, and the Polsby-Popper score. An electoral district is defined as a geographic area represented by a legislator, with district boundaries typically considering population size, geographic continuity, and community interests. A collection of districts must satisfy conditions of equal population, contiguity, and compactness. The Polsby-Popper score is a measure of district compactness, comparing the area of a district to the area of a circle with the same boundary length. This score helps evaluate how close a district is to being circular, which represents maximal compactness. A higher score indicates better compactness, while lower scores suggest more elongated or irregular boundaries. The authors propose a relaxation of the districting problem, allowing for controlled deviations in districting plans based on individual preference and tolerance. This approach enables more flexible responses to geographical and demographic challenges while maintaining the integrity of districting principles. An admissible districting plan is defined as one that satisfies three conditions: population balance, contiguity, and compactness. Population balance is achieved when the population of each district is within a specific deviation threshold of the average district population, mathematically represented as p delta I minus PAVG is less than or equal to theta PAVG, where PAVG is the state total population divided by the number of districts and theta is the maximum allowed deviation. Contiguity is ensured when a district is topologically connected, consisting of a single piece without any disjoint or isolated parts. Compactness is defined by the Polsby-Popper measure, where each district's shape must meet a minimum compactness criterion, represented as pp delta I, is greater than or equal to 1 minus kappa, pp-min, where pp delta I is the Polsby-Popper measure of district delta I. pp-min is the measure of the least compact district in the existing plan, and kappa is the minimum acceptable compactness relative to pp minimum. The population deviation threshold theta is typically set based on legal and practical considerations to ensure fairness and equality in representation. For example, a theta value of 0.05 indicates a tolerance of 5% deviation from the average district population. Geospatial contiguity in districting ensures that every part of a district is reachable without crossing the district boundary. The compactness relaxation factor kappa is set to accommodate natural and civic boundaries that may necessitate less compact district shapes. Table 1 presents information on Iowa districts, including population, population deviation, and Polsby-Popper measures, providing a real-world application of the proposed relaxation approach. Topological data analysis is a framework for examining data using concepts from topology and geometry. It aims to describe the topological structure of a dataset X embedded in a high-dimensional space by constructing simplicial complexes at multiple scales, which capture connectivity, holes, and other geometric features invariant under continuous deformations. Persistent homology is a crucial component of topological data analysis that provides a multi-scale topology of a dataset. It constructs a series of nested subspaces, xt, t element of R, filtered by a parameter t, to capture the birth and death of topological features as t varies. The persistent homology groups are defined as phk, x, equals, b, d, element of R2. B less than d and homology class, c, is born at B and dies at D, where C represents a homology class in HK, XT. The persistence interval, B, D, captures the longevity of the class, C, across the filtration. In this study, persistence in topological data analysis measures the lifespan of features in a dataset across different scales. A percentile-based method is employed to establish a significant threshold for persistence. For a persistence diagram that records the birth and death times of topological features, the persistence value for a feature is calculated as the difference between its death and birth times. Figure 5 illustrates Iowa's districting map, which is relevant to the application of topological data analysis in this study. The concepts of topological data analysis and persistent homology are crucial in analyzing the structure of this dataset and identifying significant features. In the context of analyzing Iowa's postal network, the process of identifying significant topological features involves determining a threshold value for persistence. This is achieved by utilizing a persistence diagram to obtain a set of persistence values, pi, and defining the threshold as a specific percentile p. The mathematical expression for determining the threshold is E equals quantile, pi, p, where p represents the chosen percentile. The choice of percentile significantly influences the topological analysis, with a higher percentile ensuring that only the most persistent features are considered. For instance, at a 90% percentile, the threshold value is approximately 8 miles, as shown in Figure 7. In contrast, at a 100% percentile, the threshold increases to about 14 miles, as depicted in Figure 8. The authors emphasize the importance of balancing sensitivity and specificity in the analysis, which can be achieved by adjusting the percentile value. This process is crucial for accurately identifying the topological features of the postal network and understanding its structure and connectivity. When analyzing datasets, it is crucial to prioritize persistent features while mitigating the impact of transient noise. In the context of redistricting, this consideration is particularly relevant. To illustrate this, a graph constructed from a network of postal offices is used to define a districting plan that preserves community integrity by maintaining high connectivity and induced subgraphs. KMeans clustering is introduced as a method for partitioning data into clusters, aiming to minimize the within-cluster sum of squares. This technique is particularly effective in initializing district plans in redistricting problems by clustering geographic centroids weighted by population. The algorithm iteratively improves cluster assignments and mean positions, converging to a local minimum of the within-cluster sum of squares. The convergence of K-means is ensured through an iterative process, where data points are reassigned to clusters based on their proximity to the centroid, and centroids are updated to reflect the mean position of their assigned data points. This process continues until the within-cluster sum of squares converges or reaches a local minimum. The application of K-means clustering in generating initial district plans sets the stage for further refinement and evaluation based on criteria such as population balance, contiguity, and compactness. By leveraging the strengths of K-means clustering, this approach provides a robust foundation for developing optimized districting plans that balance competing priorities. Markov Chain Monte Carlo algorithms are used to sample from a probability distribution by constructing a Markov chain that has the desired distribution as its equilibrium distribution. The state of the chain after a large number of steps is then used as a sample of the desired distribution. The convergence of Markov Chain Monte Carlo is guaranteed by Theorem 2, which states that under certain regularity conditions, the Markov chain converges to the desired distribution pi as the number of steps n approaches infinity. This convergence is reflected in the equation lim n right pointing arrow infinity sign p, x an element of A, equals pi A, for all measurable sets a subset of x, where xn denotes the state of the Markov chain at step n. The rationale for using Markov Chain Monte Carlo is to generate a wide variety of admissible districting plans, allowing for the estimation of the posterior distribution of the number of cut edges across these plans. By sampling from this distribution, Markov Chain Monte Carlo facilitates a robust statistical analysis of how likely any given plan is to occur under a set of fairness and balance criteria predefined by the model. The posterior distribution, in the context of this study, refers to the distribution of the number of cut edges after observing the data from numerous Markov Chain Monte Carlo iterations. This distribution reflects the likelihood of various districting outcomes given the constraints and conditions set by the model, such as population equality, contiguity, and compactness. The proposed methodology employs a Markov Chain Monte Carlo approach to iteratively generate and evaluate districting plans. This process involves several steps: initialization, proposal generation, acceptance criteria, and recording of results. The primary goal is to create districting plans that adhere to specified criteria while exploring the space of possible configurations to assess community integrity through minimal cut edges. The study employs the 100th percentile, corresponding to an epsilon of approximately 14 miles, to capture the entire range of topological features in the postal network. This choice allows for a comprehensive view of community structure and connectivity, ensuring that no significant community structures are overlooked, while also considering even the shortest-lived features, which might include noise. Figure 9 displays the Iowa counties, and the process involves adjusting the regions to meet population constraints while maintaining a minimum level of compactness. The algorithm iteratively reassigns counties to achieve a balanced population distribution among districts, subject to compactness constraints. The KMeans clustering algorithm is employed as the first step in the districting process to generate an initial districting plan based on population distribution and geographic location of counties. The centroids of the counties are calculated, and their x and y coordinates are extracted and stored in an array X. The population values of the counties are stored in the weights array, allowing the clustering algorithm to consider both geographic location and population size. The KMeans algorithm is applied to the data with the number of clusters set to n equals 4, corresponding to the desired number of districts. The sample weight parameter is used to weight the clustering by the population of each county, ensuring that the resulting districts are balanced in terms of population. The labels assigned by the clustering algorithm are added to the geo-data frame as the district column, indicating the district assignment for each county. This initial districting serves as a starting point for further refinement through the subsequent steps of the Monte Carlo Markov chain simulation, which adjusts the districts to meet additional criteria for compactness and contiguity. The redistricting algorithm iterates up to 1,000 times, commencing with an initial plan that ensures each district's population falls within a predetermined range. In each iteration, the algorithm calculates the total population for each district and the minimum Polsby-Popper compactness score, a measure of district shape irregularity. If districts are underpopulated or overpopulated, the algorithm randomly selects an underpopulated district and reassigns a county from an overpopulated district. The new district assignment is then checked for contiguity, ensuring adjacent counties are retained, and compactness, ascertaining the district's shape remains coherent. If the reassignment meets these criteria, it is retained, otherwise, it is reverted. This iterative process continues until a balanced, contiguous, and compact configuration is achieved, efficiently exploring various district configurations while adhering to population and compactness constraints. The authors utilize a Gaussian Mixture Model (GMM) analysis to gain insights into the distribution of cut edges in the generated districting plans. A GMM is a probabilistic model that assumes all data points are generated from a mixture of several Gaussian distributions with unknown parameters. This model assesses the likelihood of the official Iowa plan. Known variables for the state of Iowa include the population of the USA and Iowa, which are used to calculate the number of seats Iowa gets in the House of Representatives. With a total of 4 seats, Iowa is divided into 4 districts. The ideal population for each district is approximately 797,592. The parameters chosen for this study set the stage for further analysis and results in the subsequent sections of the paper. The experimental setup is defined by parameters epsilon, theta, and kappa, set to 14 miles, 5%, and 5%, respectively. KMeans clustering algorithm is employed to generate initial districts from the county maps of Iowa, where each county is represented by its centroid weighted by population size. The resulting initial districting map is depicted in Figure 10, displaying a total cut edges of 276. The KMeans clustering output is further analyzed in Table 2, which presents the district information, including population, population deviation percentage, and Polsby-Popper scores. The results indicate significant deviations in population balance, ranging from 41.63% to 46.58%. Despite this, the compactness of the districts, as measured by the Polsby-Popper scores, is relatively high, with values ranging from 0.30 to 0.51. These findings suggest that the K-means clustering approach can generate districts with varying degrees of population balance and compactness. The Polsby-Popper scores, which quantify the compactness of a district, are calculated as the ratio of the area of the district to the area of a circle with the same perimeter. A higher Polsby-Popper score indicates a more compact district. The population deviation percentage, on the other hand, measures the difference between the district population and the ideal population, with negative values indicating underpopulation and positive values indicating overpopulation. The use of K-means clustering as an initial step in the districting process is a crucial aspect of this approach, as it allows for the generation of districts that can be further refined and optimized. The results of this initial step will inform the subsequent stages of the districting process, which aim to improve the population balance and compactness of the districts. Applying K-means clustering to create congressional districts in Iowa yields initial districts with high population deviations, rendering them impractical for fair representation. To address this issue, the authors rebalance the districts using postal network data, significantly reducing cut edges while maintaining better population balance and compactness. The resulting rebalanced districting map is shown in Figure 11, with detailed information about the districts provided in Table 3. The rebalanced K-means districts exhibit improved population balance, with deviations ranging from 1.39% to 3.14%. Notably, the Polsby-Popper scores indicate better compactness and contiguity compared to the initial K-means generated districts. This approach demonstrates the potential for optimizing district boundaries to enhance fair representation and electoral integrity. By leveraging postal network data, the rebalancing process effectively minimizes population deviations while preserving district compactness. This novel approach offers a data-driven solution for creating more equitable congressional districts, ultimately promoting fairer representation and electoral integrity. The rebalanced districting plan demonstrates superior compactness across all districts, outperforming the initial K-means plan and matching the official map in terms of compactness, as shown in Table 3. A comparison with the official Iowa districting plan reveals that while the latter has excellent population balance, ranging from 0.0052% to 0.0066%, its compactness is relatively lower, measured by the Polsby-Popper score, ranging from 0.26 to 0.39. In contrast, the rebalanced districting map has fewer cut edges compared to the official districting map, as depicted in Figure 4, and a minimum Polsby-Popper score among its districts higher than the official map. The only measure where the original map performed better was population balance. Figure 12 illustrates the Iowa minimum cut edge plan observed, with a total of 315 cut edges. Table 4 presents the districts in the best configuration found by the Markov Chain Monte Carlo (MCMC) method, detailing the district population, population deviation percentage, and Polsby-Popper score for each district. The best configuration from the MCMC simulation, detailed in Table 4, exhibits population deviations ranging from 4.88% to 3.04%, with Polsby-Popper scores indicating good compactness. This configuration reduces the number of cut edges, enhancing community cohesion. Further investigation into the periodic behavior and persistent bumps in the data, figures 13 and 14, led to the possibility of multiple distributions. A BIC analysis suggested an optimal number of Gaussian distributions, n equals 3, with parameters in Table 5. The Gaussian Mixture Model analysis shows a cumulative probability of 89.10% for generated districting plans having fewer cut edges than the official Iowa districting plan, suggesting a high probability of effective districting plans. A comparative analysis of the observed districting plan's cut edges distribution reveals significant differences between the generated plans using Markov Chain Monte Carlo (MCMC) and the official districting plan. Figure 14 illustrates this comparison, showcasing that the majority of generated plans exhibit fewer disruptions to community cohesion compared to the official plan. In fact, there is an 89% chance that a randomly chosen districting plan from the generated distribution would have fewer cut edges than the current official plan. This discrepancy indicates potential inefficiencies or irregularities in the official plan's creation, which may imply non-compliance with redistricting principles. Consequently, further investigation is necessary to ensure fairness and adherence to these principles. The Bayesian Information Criterion, BIC, for different numbers of Gaussian components, as displayed in Figure 15, provides valuable insights into the model's complexity and fit. This information is crucial for understanding the underlying structure of the data and selecting the appropriate number of components for further analysis. The findings highlight the importance of using computational models to evaluate and improve districting plans, ensuring they align with redistricting principles and promote community cohesion. The need for a more systematic approach to districting is underscored, leveraging advanced statistical techniques and algorithms to create fairer and more efficient electoral boundaries. The effectiveness of topological data analysis, TDA, and postal networks in enhancing traditional redistricting practices is demonstrated through a comprehensive analysis of key findings. By utilizing post offices as population hubs, a more accurate representation of population distribution is achieved, leading to improved district boundaries and enhanced voter representation. The observed plan's histogram, fitted using Markov Chain Monte Carlo (MCMC) methods, illustrates the distribution of possible district configurations, highlighting the variability and uncertainty inherent in the redistricting process and the importance of probabilistic approaches. A Gaussian Mixture Model (GMM) overlay is applied to the histogram, elucidating the complex distribution of population data. The GMM assumes that all data points are generated from a mixture of a finite number of Gaussian distributions with unknown parameters, enabling the identification of distinct clusters within the data. This facilitates the creation of more homogeneous electoral districts and provides a more nuanced understanding of demographic patterns within each district. This enhanced understanding is crucial for policymakers and researchers seeking to ensure fair and effective electoral representation. The approach not only improves the accuracy of population representation but also offers insights into the potential benefits of leveraging advanced statistical and computational techniques in this domain. However, potential limitations and areas for future work are acknowledged, including the need for further refinement of the TDA approach and the integration of additional data sources to improve the precision of population estimates. The paper presents a novel application of TDA and postal networks in redistricting, showcasing the potential of advanced methodologies in enhancing the accuracy and efficacy of electoral representation. Leveraging persistent homology within topological data analysis, this study evaluates community integrity with unprecedented sophistication, surpassing traditional centroid-based measures. The results show that rebalanced districting plans generated using the proposed methodology exhibit fewer cut edges and better compactness scores compared to the official Iowa districting plan. However, the official plan outperforms in terms of population balance, highlighting trade-offs between different redistricting criteria. Probabilistic evaluation via Markov Chain Monte Carlo simulation reveals that the likelihood of encountering a districting plan similar to the official Iowa plan within the generated distribution is exceedingly low, suggesting potential inefficiencies or irregularities in the official plan. This warrants further investigation for fairness and compliance with redistricting principles. The study acknowledges several limitations. Data and computational constraints may impact results, as the study relies on U.S. Census Bureau and USPS network data, and the computational demands of MCMC simulations and TDA are substantial. Results are also sensitive to parameter choices, such as the percentile for TDA, population deviation threshold, and compactness relaxation factor, introducing subjectivity into the process. Furthermore, the approach may not be generalizable to larger states or finer granularity data without significant computational resources. Future work could involve integrating with libraries like Recom and GeriChain to enhance sampling efficiency, as well as investigating the optimal percentile for TDA and understanding the implications of different filtrations to enhance the robustness of the analysis. The paper introduces a groundbreaking approach to evaluating electoral districting plans by combining topological data analysis, TDA, with Markov Chain Monte Carlo, MCMC, simulations. It leverages the postal network as a proxy for community cohesion, demonstrating its application in Iowa. The methodology involves K-means clustering to generate initial districts, followed by a stochastic rebalancing process to ensure population balance, contiguity, and compactness. The results show that the rebalanced districting plans produced fewer cut edges and achieved better compactness scores compared to the official districting plan, although the official plan performed better in terms of population balance. The MCMC simulation reveals that the likelihood of encountering a plan similar to the official Iowa districting plan within the generated distribution is extremely low, suggesting potential inefficiencies or irregularities in the official plan. The study highlights challenges such as data accuracy, computational constraints, and scalability. However, it provides a robust framework for generating and evaluating districting plans. Future work will focus on extending this methodology to other states, incorporating additional community proxies, and optimizing computational efficiency. By refining these methods, the authors aim to contribute to more equitable and transparent redistricting processes that better reflect community structures and foster fair representation. This literature review delves into the application of topological data analysis in redistricting, focusing on persistent homology. It draws upon influential works by Batu and Benjo on KMeans algorithms, Carlson and Vedamo Johansson's topological data analysis, and Corcoran and Sachs's exploration of district compactness. Recent advances in recombination and Markov chains for redistricting by Deford, Duckin, and Solomon are also discussed, as well as the edited volume on political geometry by Duckin and Walsh. Furthermore, the review covers Pun, Lee, and Shaw's survey on persistent homology-based machine learning and Goudridge, Dervilis, and Wharton's introduction to persistent homology for structural dynamics. McCartan's work on finding Pareto-efficient redistricting plans, Polsby and Popper's third criterion for compactness, and Rossman's article on FEMA's use of waffle houses as a disaster response indicator are also referenced. The authors cite Traley, Saul, and Barron's Ripser.py, a lean persistent homology library for Python. This comprehensive review sets the stage for the author's subsequent discussion on the application of topological data analysis to redistricting, highlighting the significance of persistent homology in this context. The cited works demonstrate the interdisciplinary nature of this research, drawing on concepts from machine learning, data science, mathematics, and law. The accept interim proposal algorithm is a stochastic rebalancing method for K-means generated districts, ensuring proposals meet compactness and geometry requirements before validation. This algorithm takes two inputs: proposed districts and a minimum acceptable compactness score, outputting a Boolean value indicating acceptance or rejection. The process begins by calculating each district's compactness score, followed by determining the minimum score among them. If this minimum score is less than the minimum acceptable compactness score, the proposal is rejected. Next, the algorithm validates each district's geometry, ensuring they are simple and valid polygons. If any geometry fails to meet these criteria, the proposal is rejected. If all checks pass, the proposal is accepted. This algorithm plays a crucial role in maintaining district quality and validity, enforcing compactness and geometry constraints to ensure coherent and well-defined districts. This is vital for applications such as political redistricting, urban planning, and market segmentation, where district boundaries have significant implications. The stochastic rebalancing of K-means clusters algorithm, denoted as KMeans, is designed to balance district populations while maintaining a minimum compactness score. The algorithm takes as input the initial districts, population thresholds, and the original minimum compactness score, and outputs balanced districts with populations within the specified tolerance. The algorithm iterates through a series of steps, with a maximum of 1,000 iterations. In each iteration, it calculates the population of each district and determines the minimum Polsby-Popper compactness score. Underpopulated and overpopulated districts are identified, and if no such districts exist and the minimum compactness score is acceptable, the algorithm terminates. Otherwise, the algorithm stochastically selects either a random underpopulated district and samples a county from an overpopulated district to move to the underpopulated district, or iterates through overpopulated districts, sampling a county to move to an underpopulated district. The district geometries are updated after each county move, and the new district configuration is evaluated for acceptability. If the new configuration is unacceptable, the county move is reverted. The algorithm continues until no underpopulated or overpopulated districts exist and the minimum compactness score is acceptable, or the maximum number of iterations is reached. The final output consists of the balanced district populations and compactness within the specified tolerance. K-means builds upon the initial K-means clustering approach by incorporating a stochastic rebalancing mechanism to ensure population balance while maintaining compact districts. The use of the Polsby-Popper compactness score enables the evaluation of district shapes and the identification of underpopulated and overpopulated districts. The iterative process allows the algorithm to converge to a balanced and compact district configuration. In this section, we delve into the proposal generation algorithm, specifically Algorithm 3, which is designed to create new district proposals by randomly selecting a county and reassigning it to a different district. This reassignment leads to the formation of new proposed districts based on the modified assignments. The output of Algorithm 3 is then evaluated using Algorithm 4, which assesses the proposed districts for population balance, contiguity, and compactness. The acceptance criteria for the proposals include ensuring that each district's population is within a specified deviation threshold from the average population. Additionally, the district must form a single contiguous region and meet a minimum compactness criterion as defined by the Polsby-Popper measure. To validate these criteria, Algorithm 4 iterates through each district's geometry, checking for contiguity and compactness. If all criteria are met, the proposal is accepted. This process is crucial for creating balanced and coherent electoral districts that adhere to the principles of fair representation and geographical integrity. By utilizing these algorithms, researchers and policymakers can develop more effective districting plans that better serve the needs of constituents. The authors introduce Algorithm 5, Calculate Cut Edges, which computes the number of cut edges in a given set of districts and geospatial edges. This algorithm is essential for assessing the quality of districting plans. It takes as input the districts and geospatial edges, and outputs the number of cut edges. Initialization begins by setting the cut edges counter to 0. The algorithm then iterates over each edge and the geospatial edges. If an edge is entirely contained within a district, it is skipped, and the algorithm proceeds to the next edge. However, if an edge intersects with district boundaries and is not identical to the boundary, the cut edges counter is incremented. This process continues until all edges have been evaluated, at which point the algorithm returns the total number of cut edges. The authors emphasize the importance of accurately calculating cut edges, as they are a crucial component in assessing the quality of districting plans. The algorithm's logic is depicted in the accompanying figure, which illustrates the iterative process of evaluating edges and incrementing the cut edges counter. In the context of the previous pages, This algorithm is a key component in the author's proposed framework for evaluating districting plans, which also involves calculating metrics such as population balance and compactness. A two-part process is proposed to evaluate the effectiveness of Markov Chain Monte Carlo (MCMC) simulation in generating optimal district configurations. The first part, Algorithm 6, employs an MCMC simulation to minimize the number of cut edges. This algorithm iterates over a specified number of times, with an initial burn-in period to allow the system to reach equilibrium. During each iteration, new district configurations are proposed and either accepted or rejected based on predefined criteria. The algorithm maintains a record of the history of cut edges and identifies the best configuration achieved throughout the simulation. The second part, Algorithm 7, analyzes the results from the MCMC simulation. By fitting a normal or skewed normal distribution to the history of cut edges, the algorithm calculates the p-value for selecting a plan worse than the original plan. This p-value serves as a measure of statistical significance, indicating whether the MCMC simulation has found a better solution than the initial configuration. In essence, these algorithms work in tandem to optimize district configurations by minimizing cut edges using MCMC simulation and subsequently determining the statistical significance of the optimized solution compared to the original plan.